Hello, my name is Neo. I'm going to be going over homework 8, and we're going to start with problem 5.1 here. So the problem gives us that we're working with some steel, and that the minimum yield strength is 350 megapascals. And it's asking us to use distortion energy and the maximum shear stress theories to determine the factor of safety for the plane stress states. So this one's pretty straightforward. It gives you three different scenarios where you have different stresses. It gives you 100 and 100 for the stress in the X and the stress in the Y, 100 and the stress in the X, and then set negative 75 for the XY stress, and then stress in the X at 100, stress in the Y at 20, and then negative 20 in the XY stress. So just three different scenarios, and the main difference is that it just applies the formulas a little bit differently. So for distortion energy theory, our governing equations for that are going to be this sigma prime is equal to the yield strength over the factor of safety. So then the factor of safety is going to be equal to the yield strength over sigma prime. And then our sigma prime is going to be this long thing, which is the square root of sigma x squared minus sigma x times sigma y plus sigma y squared plus 3 tau xy squared. Similarly, for our maximum shear stress theory, we're going to have the factor of safety is equal to the yield strength over sigma 1 minus sigma 3. Now, sigma 1 and sigma 3 are simply the greatest and the least stresses. So it's always going to end up being sigma 1, which is going to be the largest stress, minus sigma 3, which is always going to be the smallest stress. Not in magnitude, but in like just straight up and smallest. Like if it's negative, that's the smallest. And so our governing equation for that is going to be this sigma AB is equal to sigma X plus sigma Y over 2 plus or minus, which is how we get our sigma 1 and sigma or sigma A and sigma B, plus or minus the square root of sigma X minus sigma Y over 2 squared plus tau x squared. And then when you take each scenario and you plug in your values to these equations and you fill it out in this factor of safety formula over here on the left, you'll end up getting a factor of safety of 3.5 for A for each one. For C, you'll get 2.135 for the distortion energy theorem, and then 3.5 for the factor of safety for the MSS. And then at the very end, you'll get 3.57 and then 3.365. I think it's important just to make sure that you, whenever you're doing the maximum shear stress theory, that you include the fact that there is a zero stress. And so that is, because you have a zero stress in the Z direction, so that's going to be one of your sigmas. And so you just got to make sure that you're subtracting the right two stresses. So that's the first problem. And then the next problem we're going to go over, 5.19, is fairly similar in concept. However, it goes over the Coulomb-Moore theory. And so that theory essentially follows this idea that the factor of safety is relative to this Coulomb-Moore yield strength over sigma 3. So we're going to use that same formula from up here, and then we're going to basically just plug in the values that it gives us, and then that'll give us our sigma 3. And it's always going to be the smallest number of the two in this case. So so then we come down here, and factor of safety is going to be 90, which is the yield strength that it gives us for the Coulomb. and then it's just going to be 90 over whatever we get out of this formula up here based on what we're given, and similar to the other two. And yeah, I think that one's pretty straightforward, very similar to the first question. The next question we're going to go over is 571. So in this question, we're given that it's some ASI 1040 cold drawn steel, which you can find in the textbook near the back. I think it's I want to say it's like A14 or something like that. The outside diameter is 50 millimeters, and the inside diameter is 42 millimeters. The tube is 150 millimeters long, and it's capped at both ends. And the internal pressure is 40 megapascals. And so we're trying to find the static factor of safety using the two different theories. So you have to do a little bit of recall for this one. You have to recall back whenever we were talking about pressurized chambers. So you're going to use primarily these three formulas right here. There's sigma T, sigma R, and sigma L. So this is going to be your longitudinal stress, your radial stress, and your stress along the actual theta, basically. Yeah. So you're given all the information, and you just plug that into the formulas, and then you're good to go. And then down here at the bottom, very similar to the other problems. So your factor of safety for the maximum shear stress theory is always going to be the shear strength, or the yield strength, which you can find in the book, over sigma 1 minus sigma 3, which in this case is going to be the sigma T and the sigma R here. So, and then that's going to get you 1.8. And then down here, for the distortion energy theory, it's going to be sigma prime is equal to that same formula, sigma A squared plus sigma A times sigma B plus sigma B squared. And then your factor of safety is going to be equal to the yield strength over that sigma prime, and that's going to give you 1.95. So this one's overall not too bad. It's all about just recalling this information and then knowing how to apply it to the formulas, and knowing that you don't have to actually do that formula that we saw back here in question 1 and 2. This formula right here, you actually don't need to use this, since you have all three stresses, and you're doing, instead of doing rectangular, you're doing cylindrical coordinates, essentially. So you actually don't need to use this sigma AB formula for any of that. Of course, the DET, you still do need to use it, since you're solving for a completely different value that's not an actual stress. So yeah,